Okay, I'm recording. Yay. All right, so those of you who weren't here last time, were you able to get the slides from last time? So you know to go to my website and click down to, thing, because this is not an official class, it's not supported on the Blackboard system. Have we met? We've met, yeah?
No, I missed last week.
We've met before? No? All right, well, how you doing? I've met everybody else though, right? Okay, good. Yeah, I figured that from the email address. Okay, so any questions from last time? Those of you who were here or those who saw the slides. Have you done regression before, logistic style? Good. Okay, that's good. So we're all on baseline status. And it's really hard for me to figure out how to approach this topic from baseline up without making it an entire stats class. Push! There it is. Right? And so, as you know as well, in the slides, there was a link to an illegal download site for SPSS. The illegal download site being my personal website. So if you share it, I will deny it that it exists. But it's there if you want to download the illegal copy. Because why pay thousands of dollars? And now this will be on the record, and now I can't delete it. I've got to go back and delete the audio. That's great, Ray. Okay. So let's do a little review first. So today will be a short lecture because I want some things to sink in. And I want you to think about the nature of variables again. Because the thing about logistic regression, it looks easy. It looks like, oh, you just throw the variables in and let the machine run, except you kind of got to massage the predictor variables to make them amenable to the technique and also figure out exactly what the computer is doing to each variable, because when you interpret it, it's kind of difficult as well. So review quickly for those who weren't here and for those who were here. We call this either a logistic regression, a logic regression, or a logic model. I will never use these words ever again, except for yesterday, last time and today. From now on, it's logistic regression. And we call it a logic because a logic is this polynomial of the probability of something happening divided by the probability of it not happening inside the logarithm function. So we also call log odds. Now, more about terminology. I don't know how much you remember about high school math, but ln is the logarithm with the natural base of e. So some statisticians and mathematicians say ln instead of log. I say ln, but some people say log, meaning log natural base. I was brought up log means base of 10. Complicated, I know. All the textbooks will say that the logic is the log odds of the outcome, which technically means the ln odds of the outcome. See the difference there? So when I say, anytime I use the word logarithm in this workshop, I mean ln. I mean logarithm base e, not base 10. Although if you know your math, you can convert fairly easily. Okay, straight. All right, now, if you don't understand what I'm saying, just stop me because I get mathematically pretty fast sometimes. All right, you may remember that the outcome must be dichotomous. It must be a yes or no, which usually means present or absent. We usually code present as 1, absent as 0. Even though that's a tradition, the computer expects it also. You could do 1 and 2 or 2 and 3, but the computer kind of expects 1 and 0 because the higher number is presence and the lower number is absence, so 0 absence sounds good. So is there breast cancer? The probability of breast cancer, 1 would be the breast cancer is there, 0 be it's not there. It seems obvious, but a lot of people kind of get lazy with their data. Hey, it can be coded 2 and 3, I'll leave it that way. No, we code it, just to make life a little easier. Okay, the outcome is a binary variable. This is the equation you are making, and I know that probably depresses some of you. You won't deal with that equation, just know it's there. This is the logit that we're talking about, the log odds. Odds, again, is the probability of something happening divided by the probability of it not happening. And this is what we get out of it. And this is, what's that? You know? That's a constant number. Every equation has a constant. And this is a coefficient of the log odds ratio of the first variable, the log odds ratio of the second variable, and so forth. Oh, what happened there? Hey, oh, what? How'd that happen? Okay. All right. So let's move forward. So each of these represents, when you take the logarithm of it, an odds ratio. An odds ratio is an estimate of the relative risk. Last time we went through a simple example of an odds ratio between two dichotomous variables. When you do odds ratios in class, it's always dichotomous variables. However, you can do odds ratios for pretty much any kind of variable using more exotic techniques. So logistic regression will use in the background an exotic technique to compute an odds ratio for any kind of variable, categorical, dichotomous, continuous, whatever it might be. And it tells us the risk of getting the outcome if the risk factor is present. So in other words, let's say we're modeling, again, the probability of breast cancer versus age, socioeconomic status, maternal history, whatever it might be, right? So if age is increasing, the odds ratio tells us the odds of the probability of breast cancer also increasing, right? So that's what we're looking for at the end of the day. So logistic regression allows us to compute an odds ratio for each risk factor and the outcome. What I didn't mention last time, we can also use it to compute a probability for a specific circumstance. So last time, the example I used was trying to model whether or not a candidate gets elected. And we looked at a variety of risk factors for getting elected. We looked at, is he male? Because males get elected more. Is he rich? Is he white? Is he incumbent? And all these things. Okay? Maybe what we care about is, let's say I have a candidate who's rich, female, but white. Okay, so I've got two of those criteria present and one that's not. What's the probability of that candidate getting elected? We can do that too here. I'll show that in a second. Okay, I mentioned last time that the things that we have to go through in this class to figure out logistic regression are these kinds of things. Really understanding our data, exploring all the variables, maybe recoding and things like that. Okay, as I mentioned, go to this website and look up all the good stuff. Only Elena is getting marked because you're getting this for credit. So expect you to perform. All right. So as you mentioned last time, there are a variety of types of variables. This is a review of stats. Nominal is name, categories that have no rank or value. Ordinal is ranked categories. Give me an example of an ordinal variable, somebody. GPA is not ordinal. GPA is continuous ratio. Okay, order. There is birth order is one. Or how many kids you have. How about how many rooms are there in a house? Is that ordinal? Okay, because it has rank, but also, unlike GPA, you can't have 1.5 rooms, regardless of what the real estate agent says. You can't have 1.5 siblings, right? 1.2 people makes no sense unless you're dealing with averages and things like that. Whereas so ordinal are discrete categories that are ranked. That's important because we're going to have to decide what to do with those when it comes to regression. Do we consider them to be a kind of categorical variable, or do we consider them to be a kind of continuous variable? It doesn't really matter the distinction between these two for regression purposes, so don't worry about it. That's just a continuous variable, like blood pressure, age, volume of blood, whatever it might be. Things that have rank, but also you can subdivide infinitely. You can be 5'6", 5'6.5", 5'6.75", whatever. Break it down infinitely. That's what continuous means. And the difference between these two really is, does one have a 0 or not? Doesn't matter for regression purposes. Okay, so you've probably heard of linear regression. And probably at this stage, when you're talking about regression, you probably get the two screwed up a little bit. And I want you to really make them separate in your mind. A linear regression is very much different from a logistic regression. It's the word regression that gets you. All regression means is you got a bunch of variables and you are seeing how to describe their relationship in one simple equation. We're regressing to a particular behavior. And regression, the term actually comes out of biology. Back when we used to observe the behaviors of animals, and on average, they would behave a certain way, so they'd regress to a mean. Okay, so a linear regression means we've got two variables that, on average, kind of relate to each other in a straight line. Kind of like as distance relates to time and as a car moves at a constant velocity. So the more time I'm in the car, the more distance I have. And it actually goes this way. It's a straight line pretty much. Right? So they're different in many ways. So a linear regression is modeling actual values. For example, I can predict in my stats class, my second year stats class, I can predict based upon their midterm mark what they will get in their final exam mark by doing a linear regression. And yeah, I do that by taking last year's data. I say from 2013, the midterm mark was related to the final mark in a linear regression pattern. So I would graph final mark, midterm mark, and it would be kind of like a straight line. So I know if you get like a midterm mark of 75, you're likely to get a final mark of 62 based upon those data. And I use last year's data to apply to this year's data, right? So in other words, the relationship between this continuous variable of midterm and this continuous variable of final mark is more or less a straight line. With logistic regression, that's not what we're doing. We're measuring the log odds. In fact, it's the log odds. And if you remember from last time, the relationship is not linear, it's a sigmoid. That's a straight line. A sigmoid looks like this. Like that. Does it matter to you? Not really. At the end of the day, when you interpret your numbers, that's not important. But if your examiners on your thesis ask you questions like, how would you describe that equation? It's sigmoid. And they won't ask you that question unless it's a statistician amongst your examiners, but now you know that's the shape of it. Also, the most important distinction between a linear regression or a multiple linear regression that you learned and logistic regression is the way in which the regression is computed. A linear regression uses something called the least squares method. Remember that term, least squares? Good. That's not what we do. We do something called maximum likelihood estimation. So this is least squares. That's your linear regression here. If you remember, if these are your data points, let's say again, this is midterm mark, that's your final mark, right? Let's say it's on a scale of 1 to 10. All right, so some schmuck here got 0 on his midterm, but he got like 1.5 on his final. This guy here got like 2 on his midterm, but he ended up with like 2.5 on his final, whatever. That's the display of data. And we figured out that line by figuring out the average distance from a line that minimizes all these distances. How do we minimize that distance? We take that number, we take that distance there, that distance there, that distance here, and so forth, add them all together, and see which one's smallest. But if we add a positive and a negative, they cancel out, so we square them. That squared, that squared, that squared, that squared, that squared, add them all up, see which one is the smallest number, and figure out the line. That's what least squares means. Straightforward. The nice thing about least squares is that the data's right there. Plug in the numbers, throw in a graph, done. Anything special, just one time go. But maximum likelihood is quite different. Maximum likelihood is when we take an estimate of what the relationship is, we test it, we use that testing to change the estimate, we do it again, go back and change it again. You ever learn in high school the Newton's method for computing square roots? Do you remember that? What kind of high school did you guys go to? So if I asked you to compute a square root of 17, how would you do it without using a calculator?
Think of 16.
Think of 16, get 4, then what? After that, you know, that's a good start. So Newton said, okay, you take a shot at 16, answer's 4. Then I take the difference between 16 and 17, which is 1. I take half of that, so I take 4.5, I square that, I get another number, take the difference between that and 17, take half of that, and just keep on estimating and reducing the estimate each time until I get closer and closer and closer. In other words, estimate, test, refine. Estimate, test, refine. That's really what maximum likelihood estimation is. So the computer is estimating what the best fit is, taking a shot at it, then saying, well, you know what, as this, we can get closer. Go back again, we can get closer. And does it a number of times. SPSS has a default for the number of times, and that number of times is about 20, as I recall. So 20 iterations for most regressions gets you something resembling your final model. You can keep on going, but you won't gain any more accuracy after that point. Okay? In other words, it is iterative. It's going to run several iterations. So there are different types of logistic regression. Ugh, that's horrible. Oh, it's pineapple. Okay, that's why. I thought it was just coconut water. Like, it's gone bad. When you look at SPSS, you probably already have, you'll see binary logistic and multinomial logistic. Ignore the multinomial logistic, focus on the binary logistic for now, okay? We won't touch multi-logistic. Amongst binary logistic methods, you can do it 3 different ways. Basic entry, forward selection, backward selection. These 2 are also known as stepwise approaches, and this is known as the simultaneous or standard approach. This is what you'd probably do if I didn't explain to you the nuances here, right? So people don't understand stats that well, go straight to this method. And if your data is quite simple, this is fine. All this does is shoves all the data in at once, all the variables in at once, runs it through its iterations, and it gives you a model. That's fine. But these 2 are a bit more nuanced. And with complicated health data, it's probably advisable to try one of these 2. So what this does, forward selection, is here's your outcome. Again, let's say we're modeling whether or not you're going to get elected. We're going to add on age. Run the things. Oh, we got this level of fit here, this degree of predictability that this variable gives us. Now let's add one more. Let's add sex on there. Run it. Oh, we got this amount added on. Add another one. This one here doesn't add anything extra. Dump it off. Add the next one, and so forth. So what it does is it step by step adds a variable and tests the model each time to see how good it is. And if it doesn't add some degree of predictability, it tosses it, right? This one, backward selection, is the opposite. It starts out with, yes?
Okay, so what if, does it matter the order you put the variables in? Because say that variable that didn't have predictability, what if it interacted with another variable that wasn't in the model yet, and then it would have predictability?
Exactly right. Exactly right. Yeah, forward selection has issues like that. So it matters what order you put them in, absolutely, which is why I never advise that way. Very, very sensible of you. This is what I see to be the most common way, what I use for my PhD. And backward selection, you start with all the variables in there, including the interaction terms. We'll talk about interaction terms in the future, so we know how to identify them, how to control for them. Do you know what interaction terms are? Have you heard that term before? Who's not heard that term before? Okay, good. So we have some things to do in the future then. Okay, that's good. So backward selection throws all the variables in. So we've got, again, we're looking to see if you're elected. Now we're going to throw in right away gender, age, how wealthy you are, whether you're white, all that stuff. And then takes one away to see how much it changes, puts it back in. Takes another one away, see how much it changes, puts it back in. Maybe puts it back in or not. At the end of your God knows how many iterations, you're going to have a tight model that says these are the variables that really predict our outcome with the most parsimony. Parsimony means doing it really well with the least amount of complication. So we're always looking for tight, strong, parsimonious models. You can force things in. The computer may say, you know what, this variable doesn't add anything. Toss it. You can say, no, fuck you, that's staying in. And why would you do that? Because maybe there's a reason you want it. Maybe you're measuring the relationship between electability and whiteness, right? But the computer says that's not relevant. Well, keep it in there because that's my research question. And I'm going to explore its relationship to these other variables. So you have that power to keep it in there. That's very important. Now, in the case of confounders or interactions, you must keep them in there. So you force that to stay. The computer's not clever enough to do it itself. You have to force it. So a lot of this is not cranking the numbers. It's making intellectual decisions about what's staying in. So I always recommend this one for really, robust, complicated models. However, you can still do this. In fact, what I always do after I do this and I get the variables that are strong and are remaining in it, I take those variables only, put them through here so that I get a tighter singular fit. It's all about fitness and tightness. Oh, that sounds horrible. Sounds like I'm, sounds like I'm selling lingerie. All right. So you get the idea. So those are 3 different ways of doing this. I don't recommend this. I recommend one of these 2. If you feel ambitious, go with this. If not, this will probably do you well, depending upon how extensive and large your data is. So people always ask, how many variables should I model? Do you have any thoughts on that? How many variables do you want to model? Does it matter? Yeah, what do you think? Okay. It doesn't matter. You're right. It doesn't matter to the extent that the computer doesn't really care. However, and in fact, if you wanted to really predict everything in the world, you throw everything you know in there, except a lot of variables don't offer a lot of more of influence. So why bother? We like to go for parsimonious models with the least number of important variables that tell our story. So don't confuse the issue. Get your 5 to 10 variables in there that tells a nice little story. Okay. So what are we modeling? We're modeling this relationship. If I take the log of that, this goes away, right? That's how math works. Hope you remember that. Take log of that, then this goes away. And but this is an important equation because suddenly, if I move this over there, I can predict the probability of something happening. So suddenly, instead of a model that just talks about which variables are most important, I have a model that makes predictions. And again, this is our constant number. These are the coefficients of each of our variables. So x1 might be age, x2 might be SES, x3 might be whiteness, and so forth, right? Now, what are these B1s? The coefficients. What can I do with the coefficients? Do you remember that from last time? What do the coefficients represent? What if I take the logarithm of a coefficient? What do I get? Do you remember? This is critical. The coefficient, the logarithm of the coefficient is the odds ratio, right? So let's say the logarithm of that gives me 1.5, and this is age. That means the odds ratio of the relationship between age and whether or not you're elected is 1.5, right? So that's really the beauty. I'm so excited when you do this. Oh, look, I can give you exactly how this relationship between my data and this outcome. It's very exciting. It's one of the best parts of this. Okay, so, and these are the actual values. X's are the values of the coefficients. So if I rearrange my data, I get this. Okay, the probability of something not happening is that. And right, now, if I go back there, you probably see this times that should be a product, but that product is actually with something that's a reciprocal, so it becomes a division. So that's why it is. So you can actually plug in your data now into this to get the probability of an event. It's kind of cool. So let's say, again, I can plug in all of my candidates' data. I know that how old he or she is, the gender, incumbency, and so forth, and I can figure out you've got a 16.5% chance of getting elected. Don't bother running, based upon last year's data. So that's the big caveat. Based upon the data we have, according to the model, this is your probability of being elected. Isn't that powerful? Isn't that fantastic? Are you getting excited for your own data now? Isn't that great? You can do fun things now with your data. Okay. So let's go to the odds ratio. Let's say we have an odds ratio of a relationship between the outcome is breast cancer. Breast cancer, yes or no. And you've got a whole bunch of these factors. You've got how old you are, how many kids you have, whether or not you have a family history, all that stuff. And you get an odds ratio of 1.323 for the relationship between breast cancer and number of children. What does that mean? It means this. It means for every additional child, the odds of being diagnosed with breast cancer goes up by 32.3%. Right? So it's important to keep in mind how we interpret these numbers. Everything above the 1 is an increase in the percentage odds of being diagnosed. Do you remember the difference between odds and probability? Who wants to explain to me the difference between odds and probability? What a brave class I got. Do you remember? All right. 1, 2, 3, 4, 5, 6, 7. So in a class of 7, I've got 2 men. What's the probability of being a man in this class? You give it to me in a fraction.
2 out of 7?
Precisely. What's the probability of not being a man in this class?
5 over 7.
5 over 7, exactly. Okay? So the odds of something is the probability of something happening divided by the probability of it not happening. So what's the odds of being a man in this class?
2 over 7 divided by 5 over 7.
which is
2 or 5.
2 or 5. Thank you. Right. So in other words, 5 to 2 odds that you're not a man. That's how betting works. Those are odds. So we're computing odds here, not probabilities. You can compute back, you can convert back to get the probabilities, but do not confuse odds and probabilities, which is why these numbers can be confusing sometimes. If my odds ratio were 0.9, which is less than 1, what that means is for every additional child, the odds decreases by 10%. So anything less than 1 is protective. Makes you lesser likely to get the outcome. So the computer doesn't know the difference between breast cancer and not getting breast cancer. It knows the difference between 1 and 0, which is why it's important to code that data meaningfully. So which one do you think is breast cancer? Which one do you think is no breast cancer? 1 or 0?
No breast cancer is 0.
Right, that makes sense to us. You can reverse it if you want. You can totally reverse it if you want. The computer doesn't care. But what it's going to do, it's going to give you the odds of not getting breast cancer. So you got to be careful when you compute this, what it means every time. Yeah.
Would it be drastic if it was 1, 2?
It would not be drastic, but what it means is it takes the lower number as the absence. Right?
1 would always be no and 2 would be yes.
That's right. Exactly. Yeah. Which is why we call 1, 0 situations dummy variables. Not because they're useless. A dummy usually has a 0. So we tend to like dummy variable situations. 1, 2, a lot of like, if you download data from big national repositories like CDC or Health Canada, they prefer 1, 2. And the reason for that is some statistical packages prefer 1, 2, and also because zeros confuse some people because you might end up dividing by 0 along the way, right? But if you get one of the situations, you probably have some of those, I think, you may want to consider recoding. You don't have to. But if you don't recode, just keep in mind what it's coding for. If it says breast cancer is 1 and no breast cancer is 2, it's going to make predictions towards not getting breast cancer. This screws up a lot of interpretations all the time. So get that straight off the bat. In fact, I recommend you keep a table at all times showing how your variables are coded so you can refer back to it later because you will forget. You absolutely will forget. Cool. What if the odds ratio is 1.0? What does that mean? What does that say about the relationship between having kids and getting breast cancer? Well, we said if it's greater than 1, then for every additional child, you increase your risk. If it's less than 1, for every additional child, you decrease your risk. So if it's exactly 1,
Means nothing.
exactly, nothing's going on. So 1 is the magic number here. Anything that goes towards 1 is nonsense. So remember, though, this is stats. It's not math. Even though they're kind of the same. Meaning you may get 0.98 or 1.01. That's pretty close to 1. Is it close enough to say that it is 1 and to ignore it? How do you know if it's close enough? Because you will, when you run this, you're never going to see a 1. You're going to see like a 1.1 or 1.01 or a 0.95 or something like that. And you're going to see that for like all your variables. Look, all my variables are protective. All my variables are predictive. No, because in real life, things are never exactly 1. They're just statistically equivalent to 1. How do we know if it's statistically equivalent to 1? There's another statistic to look at. Do you remember what that is? P-value. We're going to look at an example later on. The p-value tells me whether or not this relationship here is statistically significant. If it isn't, throw it away. Not throw it away, but it's not that important. Okay, so before we can do a regression, we need some assumptions. We talked about the linear relationship, so we know that there is no linear relationship between outcome and predictors. We assume that, that's fine. The dependent variable doesn't have to be normal. Remember, normal means Gaussian distribution, and every other stats you do, you say, oh, it's got to be normal, I got to check for normality. For multiple logistic regression, multiple linear regression, it's all about normality. That's fantastic, right? Doesn't matter, because it's yes or no. Who cares, right? No homogeneity of variance assumptions. What does that mean? For a lot of stats techniques like ANOVA, we assume that all the predictor variables, like the age, SES, have the same width in the data set, the same range, the same variability. And that's kind of important because if they don't have the same variability, then it skews our result usually towards finding a relationship that doesn't really exist. Logistic regression doesn't care. So it's very forgiving. And because it's very forgiving, we're very tempted to use it even when we probably shouldn't. And that's okay. For example, your data, your outcome is birth weight, is that right? Okay, so birth weight is a continuous variable. Logically, we should use multiple regression to model that. However, we know that clinicians have a cutoff between of what constitutes low birth weight and high birth weight. So you can make an artificial dichotomous variable out of that. And we very often choose to do so because then we are free to do all of this. Otherwise, if you're stuck in multiple regression land, you got to check for all these assumptions and recode all kinds of stuff. So it's probably very wise that you chose logistic regression. Is that the reason why you chose it? Yeah. Well, look at you. Nice. But the trade-off is, anytime we convert a continuous variable to dichotomous, we're losing resolution, we're losing nuance, we're losing wisdom. Also, you have to defend that cutoff. Right? Now, luckily, yours is defensible. But some other cutoffs, like, I don't know, maybe your outcome is getting enough sleep, yes or no, right? And people say 8 hours. I sleep 3 to 5 hours a night. I'm fine. So I don't need a lot of sleep. Some people need a lot more sleep. 8 hours is like a colloquial definition. That's not a very defensible cutoff. Or maybe, are you short or tall? What's short or tall? Well, 5'7", that's the cutoff for being short or tall. Well, that's a value judgment. That's not defensible. Okay, so if you're converting a continuous variable to a dichotomous variable, you got to justify it. You're okay. I think you're well justified. Maybe, depending on the nature of the population. Yeah, we'll see. We'll talk. Okay. All right. So, more assumptions. We assume that the error terms are independent. What does that mean? It means that everything in my super variables, again, for my example of are you getting elected, yes or no, and you've got age, SES, incumbency, all this other stuff, we're assuming that the errors, meaning it's the width divided by the sample size, is not dependent on each other. So if you're male, it doesn't necessarily mean that you're going to have a high income. Now we're talking about interaction terms there. Or if you're an incumbent, it doesn't necessarily mean that you're a certain color. That might not be true, right? But more importantly, it's testing for independence. So let me ask you this. Let's say my model is looking at whether or not you as an individual will, I don't know, have a headache today, okay? And I'm looking at your blood pressure, your height, your family history, all this stuff, on 20 different days. And those 20 different days are, in fact, my data. Okay? And the outcome is still whether or not you get a headache or not. Is that independent data? What do you think? Are the error terms independent there? You think so? Whether or not you have high blood pressure tomorrow, is that in any way related to whether or not you have high blood pressure today? It is. Of course it is. What you eat today affects what happens tomorrow, right? So, in other words, because all my samples are taken out of your body, then they're interrelated. There's so much interactivity there that these are not independent samples. They're quite dependent samples.
Give us an example of the independent sample.
Sure. 20 different people running for office. Almost every other example is independent. Pretty much all your studies are. Okay, let's go through this. What are you working on that's relevant to this?
Medication errors.
Medication errors, and your sample is what?
Nurses.
So different nurses. So each data point is a different nurse. Okay, and you're working on
HIV.
and each data point is a different person. And you're working on MMA injuries, each data point is a different fighter. Okay, and you're working on, I'm sorry? High blood pressure, and each data point is a different person? That's good. And you're working on birth weight, each is a different birth. And you're working on, and each one is a different person, right? Okay, and?
Genetic variation.
Genetic variations, and each data point is a different person as well. Different, ooh, in the same person? Good, okay. Now, let me ask you this. Let's say there are people in your data set who are twins, or married, or brother and sister. Is that a problem? Maybe.
Twins, yeah.
Well, maybe, yeah, especially twins. Okay, that means that things like paired designs may not be appropriate. If you got like 1,000 people and 2 of them are twins or whatever, that's not a big deal. It's really a big deal if, in fact, the design requires twins. If, in fact, you're looking at, 2 separated twins and one of them's eating cheese, one of them's eating peanut butter, and you're figuring out, which ones get diabetes, whatever, right? So the design actually has twins built into it. Or you're looking at husband-wife pairs. The design has this interaction built into it. Then we're in a problematic area. It's not impossible, it's just problematic. And we have to do some extra work to make sure it fits in well. Like separating out 2 different regressions, maybe. That's usually the way to do it. Okay, so that's the difference between dependent samples and independent samples. And each one of your variables must be collectible in and of itself. It's not dependent upon something else happening. If it is, then we combine them somehow. We'll work through some examples in the future and maybe it'll become more clear. Okay, I said that there's no linear relationship between the outcome, getting elected and any of these things, but there is a linear relationship between a continuous variable like how old you are and the log odds of getting elected. So the logit. Again, mess with your mind, right? So that sigmoidal thing, whether or not this happens, and a continuous variable, it should resemble a straight line. Okay. If it doesn't, then the risk of a type 2 error increases. Do you remember the difference between type 1 and type 2 error? All right. Think about it as a court case. So in a court case, you have a man on trial. And maybe he's innocent, maybe he's guilty. You don't know that. But the jury has to make a decision if he's guilty or innocent. Let's say he's innocent, and they say he's innocent. Yay, that's great, right? Let's say he's guilty, and they say he's guilty. Yay, that's great too. That's 2 wins, right? But let's say he's innocent, and they say he's guilty. That's pretty bad. Let's say he's guilty, and they say he's innocent. That's pretty bad too. Which of those 2 bad scenarios do you think is worse? Sorry?
He's guilty and they say he's innocent.
You think that's worse? Okay, let's say it again. So sending an innocent man to prison versus letting a guilty man go free, which is worse? Okay, so this is a value judgment. Society as a whole says that sending an innocent man to prison is worse, which is why the burden for conviction is so high. So we want to make sure that you're right. Otherwise, you don't destroy someone else's life who's innocent. So that's society. You may disagree, but that's what society says. Statistics, we tend to agree. So we say that finding that something works when it doesn't work is worse than finding something doesn't work when in fact it does. So in other words, the threshold for proof is quite high, even if it means some things get lost in the muddle. So if you're running a drug trial, for example, we would rather not identify some drugs that are really good if it means making sure that bad drugs don't make it into the market. So if we say that bad drugs make it into the market, that's a type 1 error. In other words, finding a positive outcome that isn't really positive. That's a type 1 error. A type 2 error, we would like to minimize both, but often they come at a price. They come with each other, right? Type 2 error is not finding a drug that actually works. So in a case like this, a type 1 error would be finding that this predictor variable is strongly associated with the outcome when in fact it isn't. A type 2 error would be failing to see that this thing is strongly associated with the outcome. So if I find that age is a strong predictor of, well, let's have a more obvious one. Owning a dog is a strong association with getting elected. That's amazing. We'll publish that tomorrow. Politicians will be buying dogs left and right. It'd be fantastic. But it's a fake finding. It's not really true. That's a type 1 error. On the other hand, if we find that being male is not associated with getting elected, that's a type 2 error because clearly it is associated with getting elected. So we fail to find the truth there. So violating these assumptions increases our chance of a type 2 error. In other words, failing to find true significance. It's easy to get those things confused, type 1 and type 2. But again, if you want to sound smart, use type 1 and type 2 errors. We also call type 1 error alpha and type 2 error beta. That helps. Okay, there's no easy way to test to see if your assumption's being violated. Oh, but there is. There is one easy way to test. It's this. Let us say that you suspect that one of your continuous variables is not linearly associated with the logit, the log odds. What can you do? You can do this one thing. You can convert that continuous variable into categories. Let's say, again, we're dealing with the probability of cancer, and let's say age is our predictor variable, right? And we suspect, it's age thing. Like, as I get older, the chances of getting cancer increase until I'm like 40, then it decreases. And then like at 50, it increases again. So it's not linear, right? It kind of goes, eh. That's kind of weird. So that got me worried that maybe I'm violating this linearity thing. What can I do? One simple thing you can do is to convert age into equal categories. So in this case, less than 30, 30, 60, 30, whatever, just so they're equal categories. And then you run the regression again, treating age as a categorical variable, and see what the computer gives you. If the computer is going to give you different betas, different odds ratios for each category. Now, if these odds ratios are increasing for each category at a fairly regular rate, then it's probably linear and you're probably okay. If it's like, this one's like, 1.1, that's 2.8, this is now 1.7 again, then you're probably not linear. So it's very rare that you're going to need to do this, right? Because most times there is probably a linear association between most continuous variables and the log probability of something happening. But if you're really concerned, if you're getting weird results, and you want to go by and check all this stuff, this is what you can do, okay? And let's say you do find that, in fact, the odds ratios for these categories are not increasing regularly. What can you do? Just leave it like that. Leave it as categories. And we'll see what that looks like in a second. Right? Okay, a little confusion there, but kind of with me, sort of, maybe? All right, cool. All right, so what do your predictor variables look like? We mentioned they can be continuous, like age, like your income, like your SES, like your GPA, like all these other things that measure pure numbers. But what about number of children, which is ordinal? What about number of houses? What about number of times I've been to France? I don't know. Whatever it might be. Those are ordinal. In logistic regression, we kind of wink, wink, and say, we'll pretend those are continuous. All right? Unless you've got a really good reason for not. Like, I can't think of a good reason not doing it. I really can't. So ordinal numbers can be treated as if they're continuous, in other words. And if for some reason you're getting weird results with that, just come and talk to me. We'll figure out a solution, but you shouldn't. All right. So dichotomous is the easiest thing to code. So male, female, have I been to France or not? Yes or no. Am I white or not? Yes or no. Am I incumbent or not? Yes or no. All those things. Do I have a family history? Yes or no. And again, code them as 1 or 0 as dummy variables. So the computer looks at the thing that you coded as the 1 or the thing that you coded as the higher number as being the thing that it should care about. So it's going to say, let's say you're coding gender and you say 1 is male and 0 is female. It's going to say this as maleness or not. Maleness is present or maleness is absent. Of course, to us that means maleness absent means female, but that's our interpretation. If you code it 1, 2, and 1 is male and 2 is female, it would take the higher number and say femaleness is present, femaleness is absent. Okay? It's an important consideration. So it assumes that the higher number is present. The lower number, we call that the reference level. That's a term that'll come up a lot, the reference level, reference category. So maleness as referenced against femaleness as 0. Or am I an incumbent referenced against not being the incumbent? Am I white referenced against not being white? Right? So this always wants to compare itself to something. Why? Because remember how we computed odds ratios. Odds ratios were presence, absence, got the thing, not have the thing, and create that contingency table. If you weren't here last time, it's on the slides. Okay? Because it needs 2 levels, present, absent. all the time. Categorical variables are complicated. And now we're going to look at that right now. Get that out of the way. Any problems so far with this? That's pretty straightforward? Good. All right. Am I going too slow? Everyone's kind of with me? Very good. So categorical variables are interesting. So what does it mean if we have an odds ratio of 1.5 for a relationship between breast cancer and education level? So here's education level: doctor, master's, bachelor's, high school. So in my data, I've got one variable. It's called education, and it's coded as in 4 levels: doctor, master, bachelor thing. Okay. Maybe I've got 4 numbers. 1 is doctorate, 2 is master's, 3 is bachelor's, 4 is high school. And the other day, my computer tells me there's a 1.5 odds ratio between education and getting breast cancer. What does that mean? Any ideas? Does it make any sense at all? Remember last time I said 1.32 meant a 32% chance of every additional child, but every additional what? Because I've got 4 levels here. Right? It's not ordinal, it's categorical. Well, education is a bad example maybe because you could argue that it is ordinal. Doctor is higher than master is higher than bachelor, right? But we don't, because not really. It means nothing. And we'll get to that one in a second. Categorical variables can either be coded as indicator variables or deviation variables. What does that mean? It's a lie, first of all. They can be coded as many things, but I want you to only consider indicator and deviation. In SPSS, if you go to Analyze Regression, Logistic, you can select your variables for your regression, put them in the right boxes. Hopefully you've done this already to play a little bit. And you can, if it's a categorical variable, it needs to be told. It doesn't know automatically if it's categorical. All right? So you've got to highlight it and check and select categorical. It's then going to open up another window and say, change contrast. Contrast is this. The default is indicator, and that's probably what you always want. You probably always want indicator, and I'll show you what the difference is in a second. It's also going to ask you what the reference category is. The default is last. You probably always want last as well. Okay? Remember what I said just now, if 1 is male and 0 is female, 0 is the reference. So 1, maleness is present in reference to not being present, being female. This is what it's looking for. It's looking for what to refer to, what to compare all the other elements in the category to. So for education, doctor, master's, bachelor's, and high school, what do you want to compare everything to? You got to choose one of those. Everything in that variable is going to be compared to a level in itself. What do you think is the rational thing to compare it to? Doctorate, master's, bachelor's, high school. In other words, what's the baseline? There it is. Everyone shouts that. Right on, right? I would tend to agree. The computer doesn't know this. It doesn't know the difference between these things. You have to tell it. So in other words, doctorate versus high school, master's versus high school, bachelor's versus high school. You can't do these two, then these two, then these two, and these 4, or this versus that, or that versus these. You can't do that. You got to choose one to compare the rest to. That's why categorical is so problematic. The same way, if I'm doing a male and female, it's the same thing. It's male versus that. So it's just one step beyond. I've added another category. Maybe transgendered versus that, males versus that. Here it's education, that versus that, that versus that, that versus that. That's the indicator method. The deviation method is slightly different. So deviation compares categories to average effects. I don't recommend it. It's confusing. So in this case, it would be doctorate versus like average education, or master's versus average education. How useless is that? To me, it's useless. It's useful for specific situations, usually in bench sciences or in like physics and things like that. But in population level stuff, indicators what you want. Right? So here, doctorate 1, master's 2, bachelor's 3, select level 4 as the reference. You can set that in SPSS. If you don't, it'll take the last one as default as the reference, right? So this gets compared to that gets compared to that, this gets compared to that. So Our odds ratio of 1.5 means nothing, but that's not what it gives you. The regression output will give you an odds ratio estimate for each level of the categorical variable. Thank God. So let's say it says 1.5 for the doctorate. What does that mean? It means you have a 50%, 0.5% higher odds of having breast cancer if you have a doctorate versus having a high school education. Right? Not versus not having a doctorate versus having a high school education. It's a very important nuance when it comes to interpreting your data. So here's an example. SES. Its code is 1, 2, and 3. And this is how, when you do it, it's going to give you a table that summarizes how you code your data. So SES is 1, 2, and 3. 1 is low, middle, and high. This shows you how many cases in your data set you have. And then it shows how it has coded the dummy variables. 1 is SES1, 0 is SES2, and nothing is SES3. That means nothing too, but at the end of the day, when you run your regression, this is what it gives you. Let's look at what these elements mean, because very soon you'll be looking at the regression outputs, and it's going to confuse you and probably scare you. So it's going to give you the variables at the end of the equation. It's going to give you a whole list of calculations up here, each one representing each iteration. Remember, because the maximum likelihood estimation method takes an iteration effect. This time, 20 times probably. At the end of the day, it's going to tell you, if you've done a backwards stepwise, for example, I took out this garbage and I'm stuck with these guys. These are the ones that I think belong in the model. Okay, so let's look at this. In this data set, it's a data set looking at whether or not someone got a certain score on a test. Okay, and this is the reading score, the science score, the SES, and the constant. Look at SES. Even though there's one SES variable, it's given you 3 levels here. This is the general SES variable. Means nothing. These 2 are the first 2 here, low and middle. It doesn't give you high. It doesn't give you the third one. Yes?
What does SES stand?
Oh, sorry. Socioeconomic status.
Oh, okay.
Right? So it doesn't give you, why doesn't it give you the third one? How come the third one's not there? What would you compare the third one to if it's the reference category? Nothing. It's meaningless. So that's why with categorical variables, you kind of lose a little bit of insight because you don't get that last guy, right? So here we find out, let's figure out what each of these means. B is your beta, the coefficient in that equation. How do I get my odds ratio from that? If that's the coefficient in my equation, odds ratio is what? Exactly, the log, the natural log, the ln. So you take the log of that and you get, right. Okay. I'm trying to remember, is it log or is it e to the thing? It might be e to that, well, whatever. I'll figure it out later. I'm better rested. Okay, but yeah, you got to transform that to get your odds ratio. This is the standard error. That can be useful later on, but not necessarily. This is the Wald statistic. Wald is, don't worry about it too much. It relates to the way that chi-squares are distributed. But the Wald statistic is computed for you to tell you how significant your odds ratio estimate is. So this p-value here is derived from that. Okay? So when it comes to, you can probably ignore this for the work that you're doing, but focus on that. Oh, it's not the log. It's e to the thing, right? Because the log odds are already given. So e to the beta gives you your odds ratio. Because that's given here too. Thank God. Right? So in earlier editions of SPSS, it didn't do it for you. You have to do it manually. Why didn't they do it for you? Luckily, it does it for you right now. So that's the beta. That's the odds ratio. Right? So suddenly, we find out that for as reading skills increase, it gives you like a 10% increase odds of whatever the outcome here is. I think the outcome is getting a certain mark. I forgot what it is. Okay. So of the significant ones, if your cutoff is 0.05, as it usually is, these are all significant, except that one's not. What's it doing there? This is SES1. What's it doing there? I'll tell you what it's doing there. This is one level in one variable. I can't just pull out one level out of a variable. If anything in that variable is significant, the whole thing is significant. Oh, hang on, what happened there? So the second one, that is significant. So SES2, that's significant. Therefore, everything goes in to the final model. Right? And the reason for that is these are not standalone concepts. They're comparing to this high level. So SES1 as compared to 3 gives me that odds ratio. SES2 as compared to 3 gives me that odds ratio. SES3 as compared to itself doesn't matter, stays out. That's why categorical variables can be a difficult thing to wrap your brain around. That's, so give it some time. That's the last slide of new stuff. Any questions, any clarity? This is what you do. Okay, so for your homework, to play with this, there's another data set now uploaded onto the website, right? And it's actually the data from this. And it describes high school students' demographics, SES or age, so for and their marks. So I want you to impute an outcome variable for coding whether or not the student got a mark of 60% or greater in the writing class. So this will test or allow you to experiment on how to impute a variable. To impute a variable means create a variable. So use the compute function on SPSS. So if mark is this, then equals this. It's going to be something like if writing mark 60% or greater, then HonCom equals 1. If mark is not, then HonCom equals 0. So create a binary dichotomous outcome variable called HonCom, right? So what must we do with the writing variable? We must break it down. This is now your dichotomous outcome for writing a logistic regression. So I want you to explore whether or not the log odds linearity assumption applies for the continuous variables. What does that mean? It means breaking down the continuous variables into even categories, running the regression, and seeing if the betas are equally progressing sizes. That's all it is. Just play with the assumptions we did with today. So I want you to run a sample logistic regression, and if you want, you can try it forwards and backwards and all that crap. Get used to it, that's all. Play, in other words, just play. Next week we'll do some more. Any questions about today's nonsensical blabberings about, no? Cool? I can't tell if you guys are following along or not. You're bored, or, all right, cool. All right, good. No. All right, good enough. And I'll post the audio once I take out that earlier reference to illegal downloads on YouTube.